probably hear some alarms when you have 3 minutes left. Please.
Thank you. Okay. Thanks for the time for me. Today, I want to share our research about the constructive learning and ensemble BERT for identifying and categorizing offensive language in social media. We are a team consisting of me, Fajar, and informatics student of ITB, and also our supervisor is Ibu Purwarianti and Ibu Fariska Zakhralativa. And before we started, I want to introduce some of what we do in this research. We started with the problem. Today we know that social media is necessarily a needing for everyone in the world, and the user of social media is increasing year by year. And now we know that one of two people in the world is a social media user. But when the social media user is increasing, some of people is often abuse the freedom of expression to carry out some offensive actions, such as cursing or using the offensive language to hurt each other. And then in the semantic evaluation conference 2019 task 6, the conference is proposed to tackle this problem, to tackle the offensive language issues on social media, to create the social media climate conducive. This is the offense eval. Offense eval is the task to identify the offensive language. There are 3 subtasks in the offense eval. The first subtask is subtask A, which classify the sentence into offensive and not offensive. And when we know the tweet is offensive, we move to subtask B to classify whether the tweet is targeted or untargeted. And then when we know that the tweet is targeted, we move to subtask C to know what is the targeted tweet about. Is it to individual or group or others? In this research, we use the dataset called the OLI dataset or offensive language identification dataset. The dataset contains the tweet. This is the first row is tweet, and then the other column is the respective labels for subtask A, subtask B, and subtask C. And when we look deeper in the dataset and also read the paper about the previous work, we face the some of problems in this research. We know that the Twitter dataset, the OLI dataset is constructed use the tweet which contains informal language, abbreviation, emoji, hashtag, and also masking for some of words. And also the second problem is sentence semantics. We know that some of words is maybe it's offensive, but when the words when the some of words in the sentence, they become unoffensive or not offensive. For example, the word fucking, we know the word fucking is offensive, but when the word is sentence, maybe I'm fucking loving this cat. It means that it's not offensive. And the second and the third problem is that imbalance dataset. In the OLI dataset, we know that this imbalance dataset with ratio in subtask A 1/2 and in subtask B 4/1 and in subtask C 18, 8, and 3. And then the last one problem is BERT irregularity. We face the BERT irregularity when we want to reproduce the previous results. We face the problem that when we use the different with initialization and then we use the different hardware may result in the different result. Okay, and the solution for this problem is when we use the dataset Twitter, we use the preprocess. When we use the preprocess And also the solution for the sentence semantic, we use the BERT model, which BERT is uh, is the model to know the semantics of the sentence and see the sentence as a whole. And the other reason is for from the previous works, top 10 teams that achieve a state of the art performance in the audit dataset research is using BERT and the modification of BERT. And then the solution for imbalance dataset, we use cost-sensitive learning by modifying the last layer of the classification layer in top of BERT. And then for the BERT irregularity, we use Ensemble to tackle of the problem. What we do in this research, we are identifying and categorizing offensive language in social media by developing the cost-sensitive learning and Ensemble BERT to improve the existing models. In this research, we produce a model with the configuration to improve the performance. Okay, I want to move to next section is implementation and experimentation. This is our architecture in this research. For example, we use data source only dataset. Then we doing pre-processing to pre-process this dataset, and after that we have the dataset after pre-process. Then we doing modeling by use BERT 1, BERT 2, BERT 3, and so on. And we use a lot of BERT models in here. And this BERT actually is the same model, but the same model with the same parameters, but they different in the weight initialization. As we know that when we have to classify the sentence, we just adding one layer in top of BERT, and then we just initialize the weights and updating the weight during the training. And after that, every BERT will produce the output, and then we ensemble this output from previous BERT. We ensemble with the hard majority voting and soft majority voting, and we will decide the best method of doing ensemble in this experiment. Okay. The pre-process module consists of converting emojis to English sentence, hashtag segmentation, and change the string URL to HTTP, because the URL does not exist in the BERT tokenization. So we use we convert the URL to HTTP and remove some mutation and limit to a maximum 3 consecutive ad user and change writing to lowercase. And this is the BERT module. This is the visualization of BERT module. When the BERT originally they use the cross entropy loss also, but they don't take care of the imbalance classification problem. And in this research, we change the loss of the BERT by using the cross entropy loss with modification the class width. To know deeper this, let's see the formula. The original loss function is in the left side, and the modified loss function is in the right side. Simply we multiply the loss function with the weight that we inputted to the model to give the more penalties to the false classification in the minor classes. And in the Ensemble module, we use the soft majority voting. As we know that soft majority voting is to some of its level in here, and then we have the resulting here, and then we just see how what is majority class in here, and the majority class is individual with 1.9 result. And the hard majority voting here is it's example of calculation of hard majority voting here. And then the experiment want to things to observe is pre-process method, cognitive learning on BERT, and also what is the best ensemble technique in this research. Okay, I will start from the validation data for experiment A. In this slide, I just adding the top three of class width, and the last one is the worst performance. And we can see that the class width or the use of consecutive learning is increase the model, but it doesn't really difference between when we don't use class width or not. And then for the ensemble technique, we see that had majority voting produce the more the best result compared to the soft majority voting in this case. And for the experiment B, we may see that to recall the level distribution in subtask B, we have the level distribution that around the ratio is around 1 and 4, and when we use the class way to doing consecutive learning, we can see that when we have the very imbalanced level distribution, the consecutive learning may give the better result, and we see that in here the consecutive learning may improve the performance by 7%. And for the validation data for in example technique, shows that hard majority voting still better than the soft majority as in subtask B. And in experiment C, it is experiment for subtask C. We see that the class width and consecutive learning is incredibly improve the performance. This is the top three, the top three for the top model, and the last one is the worst performance. And we can see that improving it's improving a lot here. And then for the data validation,
3 minutes.
Okay, thank you. For the data validation in experiment C, that it's hard majority voting still better than the soft majority voting. Okay, then I will use comparison. This is the result of the testing method, and the testing doesn't follow the validation data. And when we test the data, it's like the overfitting. We can see that it's decreasing from the baseline to consecutive learning because the consecutive learning doesn't really do anything, because the difference relatively small difference in validation data by using consecutive learning or not, the improvement only 0.04%, and then in test it's overfitting. And then when we use ensemble consecutive learning, it's increasing the performance. And in the subtask B, the ensemble and the consecutive learning is good enough with this result. We get the first place within the current state of the art is 0.755. And in the subtask C, the use of cost-sensitive learning is best for the subtask, but the use of ensemble is decreasing the progress model, because the after inspecting our composite model for the ensemble, the best model for the cost-sensitive learning configuration doesn't include in the ensemble. This is maybe the how we choose the model to the ensemble. It's can be a future work of our research. And this is the conclusion of our research. we know that constructive learning technique is best for imbalanced dataset level distribution, such as OLE dataset that I saw before, and then the ensemble technique may improve the performance if the model using the composite model is correctly selected, which means we 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 have to correctly select what the composite model or the ensemble consists of model E, model B, and model C, and so on. Okay, thank you for this time. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for the presentation. I will refer back to the audience whether there are any questions or not. So far, there's no. So the conclusion would be that the ensemble didn't really help much for the random seed initializations. I mean, it doesn't really helps. Yes. Okay. And what was again this cost sensitive? For the subtask A is it's only on the subtask B and C, but the imbalanced dataset cost sensitive learning didn't really helps on subtask A. Can you re-explain it again?
Okay.
Why this happened?
Okay. We may. I wanna back to my slide. Okay. Okay. This is clear enough when we have the imbalance clearly imbalanced on subtask B and subtask C, where
yes,
imbalance enough, and in the subtask A, the level distribution is imbalanced, but it's not significantly
not so
different.
contrasted. Yeah.
Yes. Maybe it's
I see.
Yes, I saw.
And the result was really not. I mean the end result was not really that far from the state of the art. Yeah. Okay. Let's see if there are any other questions. No, so far. And okay, that would be what is the BERT model that you are using?
Okay, thank you. Thank you very much for the question. And the BERT model that I use is BERT-based model, and the BERT model is actually when I use the higher BERT model with the more parameter and the more weight, the more layers, I can just get the better result. But this purpose of this research to compare with the previous research. The previous research used the BERT-based model, and the I wanna improve this approach to use the fine-tuning BERT by applying the constructive learning and ensemble method in the same of BERT variant.
Okay. I think that's good enough. So this one, the baseline would be the uncased, right? Or it's it's the uncased one. Okay.
Yes.
It's the uncased one. So we use the case non-sensitive since you have some pre-processing that part. Okay. So let's see if we have another question. Not so far. So thank you again for Fajar for presenting this interesting